Stefan, are you ready?
Yes.
Okay, welcome back, everyone. Our next speaker is Stefan Wenger, who will be speaking about isoperimetric inequalities and curvature bounds.
Okay, first of all, thank you very much for the kind invitation to this very interesting conference, and I'm really sorry I can't be there in person. So in this talk, I would like to explore a bit relationships between isoperimetric inequalities on the one hand and curvature bounds on the other. And most of what I'm going to be talking about is joint work with Alexander Litchak, and some is also in collaboration with Robert Young. And I apologize already, these are not my most recent research results, but I think they fit better to the theme of this conference than, so I'm going to present them anyway. So this topic of relationships between isoperimetric inequalities and curvature bounds is quite classical and has quite a rich history, but most results, especially the classical ones, they go in one direction. They try to establish, given a curvature bound, they try to establish isoperimetric inequalities. And I'm mostly interested in the other direction. You know, suppose we have a space with a certain isoperimetric inequalities, equality, and for me, this is always going to be for curves. You know, what can we say about the geometry of the underlying space? Let me maybe start with the following very classical result for two-dimensional Riemann manifolds, which characterizes an upper curvature bound by an isoperimetric inequality. More precisely, if the curvature of a two-dimensional Riemann manifold is bounded by a certain real number kappa, then every Jordan domain in M satisfies the following isoperimetric inequality: 4 pi times the area of the Jordan domain minus kappa times the area squared is bounded by the length squared of its boundary. And moreover, equality holds if and only if omega is a geodesic disk of constant curvature kappa. So this was established in various generalities, first, I think, by Beckenbach-Rado in around 1933, then by Fiala, Ball, Alexandrov, etc. And there's also a converse, namely, if we have this isoperimetric inequality for every Jordan domain, then necessarily the Riemann manifold must have curvature bounded by kappa. And actually, the converse direction is the easier one because we have asymptotic formulas for the length of a small geodesic circle around the point and the area of the geodesic disk, you know, in terms of the curvature. Okay. And Reshetniak and Alexandrov, they actually generalized this also to surfaces with bounded integral curvature. Noteworthy, if kappa is equal to 0, then of course we just get the Euclidean isoperimetric inequality. Then this term here, of course, vanishes. And if kappa is strictly smaller than 0, so if you have negative curvature, then for Jordan domains with large length of the boundary, then we get something much better, namely the area of the Jordan domain is bounded by the length and not by the length squared. Okay. Now we can also make sense of an isoperimetric inequality for curves in higher dimensional spaces, simply by asking, well, given a curve, you know, how much area for a surface with boundary this curve do we need to fill it? Okay, and we will say that a metric space has the Euclidean isoperimetric inequality if every Lipschitz curve has a Lipschitz extension to the unit disk with area bounded by this Euclidean inequality that we saw before. Now, what is area? Well, area is the parameterized area, which, well, when X is a smooth Riemann manifold, for example, or a normed space, well, then we know by Rademacher's theorem that U is almost everywhere differentiable, and then we can just integrate the Jacobian. Now, when X is a general metric space, then Lipschitz mappings from the unit disk or Euclidean domain, they still have metric derivatives by Kirchhein's Rademacher theorem. And so this is a semi-norm based on R2 in this case here, and which measures in every direction, basically measures the infinitesimal distortion of the map. and we can still define a Jacobian, a suitable Jacobian of this semi-norm, which I denote by this, and then we define the area by this. And so by the so-called area formula, this is simply the Hausdorff-2 measure of the image of U counted with multiplicity. So in particular, when our map U is injective, then it's just the Hausdorff-2 measure of the image of U. So more generally, we'll say that the metric space X admits a quadratic isoprimetric inequality for curves with a constant C, if the same thing holds when this factor, this Euclidean factor 1/4 pi, is replaced by this constant C. Okay, and of course now the question is, well, you know, suppose a space has a quadratic isoprimetric inequality for curves with a certain constant. What can we say about the geometry of the underlying space? Let's go first in the classical direction. So when X is a cat-zero space, well, then it has the Euclidean isoprimetric inequality for curves. And this basically just follows from Reshetniak's majorization theorem, which we've already encountered, I think, in this conference. Well, given a curve, a Lipschitz curve in X, well, then by the majorization theorem, it's majorized by a convex subset in R2, which means that there is a convex subset C and the one Lipschitz map from C to X, such that on the boundary, this one Lipschitz map is an arc length preserving parametrization of the curve. Okay, and now since R2, of course, has the Euclidean isoprimetric inequality, you know, and one Lipschitz maps, they decrease the area, we get this. And now, what about the other direction? Okay, so suppose we have some quadratic isoprimetric inequality for curves. What can we say about the space? And the first theorem I want to present is that, well, when we have the Euclidean constant, and this is my first result with Alexander Litschak, which basically characterizes, at least in the case of proper metric spaces, so metric spaces where bounded and closed subsets are compact, they characterize cat-zero spaces by a Euclidean isoprimetric inequality. Okay, together, of course, with Reshetniak's theorem. And there's an analogous result also for other upper curvature bounds, and there you just compare basically with the isoprimetric inequality you have in the model space, so the hyperbolic plane of curvature kappa when you have negative, or the sphere of curvature kappa when this is positive. Okay. Well, when you try to prove this theorem, I'm going to sketch the proof in a little while. Then, of course, the first thing you should check is, well, what happens, for example, in normed spaces? So, for example, in two-dimensional normed spaces, what kind of isoprimetric inequalities do they have? And here is what we can say. So this is basically an application of what is called the Blaschke-Santalo inequality, which says that when you take an isoprimetric set in a two-dimensional normed space, so this is just a convex set with the biggest Hausdorff measure with given perimeter, well then, you know, the Hausdorff measure is always bigger or equal to what you have in Euclidean space. And equality holds if and only if this two-dimensional normed space is Euclidean. So there we're lucky and we get that. Maybe a word of caution. So this Blaschke-Santalo formula is something from convex geometry, and there's other definitions of area in convex geometry, such as for example, the Holmes-Thompson area or volume. And actually, you can also define, of course, now the parametrized area with respect to another definition of area, but then actually the theorem doesn't hold anymore. Because, for example, if you've replaced the Hausdorff measure by the Holmes-Thompson area, then you will have equality for every normed plane. Okay, so here it's really essential that we have the Hausdorff measure, yeah, and not any definition of area as from convex geometry. Okay, now what about higher dimensional normed spaces? Well, a nice result of Polkreutz, a recent result, says that, well, they have a quadratic isoperimetric inequality with constant that is always between 1 over 4 pi, the Euclidean one, and 1 over 2 pi. And actually, for every constant in between there, you get the normed space where you have this isoperimetric inequality. So where you have really, that's the optimal one. Okay. So you might ask, well, what about, for example, if you have smaller isoperimetric constants, so smaller than 1 over 4 pi, what happens there? Well, the only spaces that satisfy that, so to say, geodesic metric spaces are actually metric trees. So cat minus infinity spaces. And these, of course, right, they're the isoperimetric inequalities, even trivial, because every area of a Lipschitz disk is actually equal to 0. So somehow, maybe surprisingly, that once you go below this Euclidean thing, you collapse immediately down to metric trees. I'll explain the outline of this theorem above here a little bit later. Let me just mention now what is the basic idea. So the basic idea is as follows. We know that minimal surfaces, at least in a smooth setting, they inherit the upper curvature bound of the ambient space. Okay. Now, the idea is to somehow reverse the direction. We would like to use this Euclidean isoperimetric inequality to show that every minimal surface, whatever that means in X, in this metric space X, has non-positive curvature, is cat 0, and then conclude from there that X actually must be cat 0. Okay. So before I explain this in more detail, I would like to give some coarse versions and asymptotic versions of the theorem here, and also maybe of this theorem here. And for this, it is convenient to use the Dehn function or the isoperimetric function. The Dehn function is an important invariant in analysis and geometry, and especially in large-scale geometry and geometric group theory. And more or less, it measures how much area you need to fill a curve of length r. So for a Lipschitz curve in X, the filling area of this is just the smallest area of a Lipschitz extension of this curve. And then we can define a function, the Dehn function, I'll call it the Lipschitz Dehn function or geometric Dehn function, which then, just looks at all curves of length at most r and chooses the one that is most difficult to fill, okay? So for example, in Euclidean space, right, so circles, plane circles of length r are the most difficult to fill. They have filling area just, well, the Euclidean constant 1 over 4 pi times r squared. And so the Euclidean isoperimetric function is just 1 over 4 pi times r squared. And now the results that I presented, so Reshetniak and then our converse, they basically just say that a proper geodesic metric space is cat 0 if and only if the Dehn function is bounded by the Euclidean Dehn function at all scales. Maybe I should just say one word about proper, okay? Well, usually in cat 0 spaces, right, one does not need any local compactness to do arguments because there, the convexity of the metric helps us, okay? Here, we don't know yet actually whether our result holds for any complete geodesic metric with a metric space with a Euclidean isoperimetric inequality. And somehow the problem in the proof is as follows. Well, I said something about minimal surfaces in X. Yeah, so the problem is that when it's not proper, and we will have to try to construct minimal surfaces with a given boundary, and this we can do when we have a local compactness assumption, but we don't know how to do it in the general case. Okay, so just in a nutshell, we have this. Now, I've already said that the Dehn function is an important invariant, and this is because it's a quasi-isometry invariant in a large class of metric spaces. So start with two proper geodesic metric spaces, X and Y, and suppose they're Lipschitz one connected up to some scale. So this just means that Lipschitz curves of small length, they have a Lipschitz extension with a linear control of the Lipschitz constant. Okay, and this is, at least when you talk about quasi-isometry invariance, this is not a very restrictive condition, because any such metric space which is proper and geodesic is actually roughly isometric, or in particular quasi-isometric, to a proper geodesic metric space which is Lipschitz one connected up to some scale. And this is basically just try to thicken up your space a little bit so that small curves can be filled. And there one uses constructions involving injective hulls that Ursula already talked about yesterday. Okay, and then in this class of metric spaces, the Dehn function is a quasi-isometry invariant. So if X and Y are quasi-isometric and the Dehn functions are at every scale, they're finite. So in some sense, this means that you don't have any holes. And then the growth of the respective Dehn functions is the same, the asymptotic growth. And moreover, if a finitely presented group acts geometrically, so properly discontinuously and co-compactly by isometries, then the Dehn function of the space has the same growth as the combinatorial Dehn function of the group, which basically measures how difficult it is to write a word which represents the identity of length at most R, can be written as a conjugate of relators. Okay, so when X and Y are basically co-compact Riemann manifolds or finite dimensional simplicial complexes, this result was already known, goes back to, I think, Burillo Tabak and also to Breitzen. And usually how you try to prove this is, well, you take a good triangulation and then you try to push curves into the one skeleton, and then you use things like this. Okay, of course, in this setting here, you don't have triangulations, and this deformation theorem of Federer-Fleming doesn't exist. But here we can actually use similar methods as in the proof of the main theorem that I presented already. And so in this general case, the result is to Alexander Litschak, Robert Young, and myself. Now, an important theorem of Gromov is the following. Gromov showed that Gromov hyperbolic spaces, they can be characterized as those that have a linear Dehn function. Okay, so one direction Gromov hyperbolicity implies linear Dehn function is relatively easy because one can efficiently cut up curves, and the other direction is a lot harder. And actually, Gromov shows something much stronger. He even shows that if the Dehn function is bounded from above by a very small constant epsilon times r squared for all r sufficiently big, then X is Gromov hyperbolic and thus has actually a linear isoperimetric Dehn function. In particular, no metric space, geodesic metric space, can have a Dehn function that grows somewhere between linear and quadratic with a small constant. Okay. Now, some related asymptotic results to this result of Gromov and our main result is the following. The first one is basically a sharp version of Gromov's theorem. which I proved a long time ago. It says that if you have a geodesic metric space where the Dehn function asymptotically grows somewhat smaller than the Euclidean one, then x is already Gromov hyperbolic, and the Dehn function is thus already linear. Now, of course, one can ask, well, what about if we replace, the strict inequality by an equality? And now this is somehow the relative, the coarse or the large scale analog of our theorem with Alexander. So if you have a proper geodesic metric space where the Dehn function asymptotically grows at most like the Euclidean one, just asymptotically, then of course on small scales you can't say too much, but on large scales the space looks cat zero. So in other words, every asymptotic cone, that means you blow down the space and you pass to an ultra limit, to a certain limit, then this is cat zero. Now, the idea of the proof of this theorem is similar to the one that we already saw, the main result. So the first observation is, if you, in this Dehn function, if you place all the Lipschitz maps or on the disk by Sobolev maps, then you get the so-called Sobolev-Dehn function. And this has good stability properties, namely, a quadratic upper bound passes to ultra limits. Okay, so in the asymptotic cone, we then, and with the same constant, so in the asymptotic cone, we actually have a Euclidean isoperimetric inequality for this, or upper bound for this Sobolev function. Okay, but the problem is that this asymptotic cone is not necessarily, or in general, will not be proper, right? And so I already said we need properness to solve Plato's problem. Okay. So the main somehow task you have to do in order to run the proof is to show that you can still solve Plato's problem. So constructing a candidates for area minimizers, this is not so difficult. There you can use some compactness theorems for Sobolev mappings, etc. But the problem is afterwards to actually show that this is really an area minimizer. Okay, so you have to construct competitors, and this is somehow, but this you can do when you have this Euclidean upper bound. This works. So in the statement one, right, we actually have a characterization of Gromov hyperbolicity, but in statement two, this is not true. So the converse is not true. Namely, one can construct a metric space which is even bi-Lipschitz homomorphic to R2, which has exactly one asymptotic cone, a unique asymptotic cone, which is Euclidean R2, but where this inequality here fails. Okay, and the idea, one way one can do this, one starts with what's called a pinwheel tiling, and then one replaces all the tiles by little spherical caps, and then one wants to show that the asymptotic, unique asymptotic cone is R2. Okay. Now, so we know now what happens for isoperimetric constant at most 1 over 4 pi, and we also have large scale versions of these results. So what about if we have a higher, a quadratic, an isoperimetric constant, which is bigger? Okay, so when it's only slightly bigger than the Euclidean one can still say something little. Okay, namely the following. So for every real number nu strictly positive, there exists an epsilon, so that if the isoperimetric constant is just a little bit bigger than the Euclidean one, say just on a scale 0 to R0, then geodesic triangles of perimeter at most, a little bit less than the R0, they are cat nu times the perimeter. What does that mean? This means that, well, in the cat zero inequality, right, if you look at a comparison triangle, then the distance between 2 points is bounded by the distance in the comparison triangle plus an additive error term. Okay, so this inequality, this basically says that, well, or triangles that are close to equilateral, you know, they're almost cat zero, right? But of course, if here the length, the upper length here is very small, so if you have a relatively thin triangle, then you know that means it can be relatively thick. Okay, so this result says something in something that is maybe interesting, I don't know, for equilateral triangles, but not for thin triangles. So this term cat nu, say 0, was, I think, termed by Gromov, and then, for example, studied by Aditi Kar. Yeah. Okay, now what about arbitrary isoperimetric constant? Okay, so there we can say much less. Okay, and the only thing that I know at the moment is the following. Start with a proper geodesic metric space. And suppose that the Dehn function is bounded by an arbitrary constant times r squared. Then for every alpha strictly smaller than 1, alpha Hölder maps defined on subsets of R2 can be extended to all of R2, with a linear increase of the Hölder constant. Okay, and of course the linear term here does not depend on A, but it depends on alpha and the constant C. Okay, so in particular, if you take a lambda Lipschitz curve, then it extends to lambda L Hölder map on the unit disk. Okay, and now recall, of course, a Lipschitz, a cat zero space is Lipschitz n connected for every n. So that means Lipschitz maps from n spheres can be extended to the n plus 1 ball with a linear increase of the constant. And here we get at least for n equals to 1. So for the circle, we get something that is a little bit related. For higher spheres, we can't say anything. For example, if you take a higher Heisenberg group, so the topological 5-dimensional one, this has a quadratic Dehn function. Okay. And actually, you know, it's Lipschitz 1 connected, but it is not Lipschitz 2 connected. So the proof here uses again similar elements about area minimizing disks in metric spaces and so on. And I'll say a word about this. And actually, similar techniques can be used to produce Hölder extensions in the Subriemann Heisenberg group, and even in more general Karner groups. And there, you know, maybe you know that a famous problem of Gromov's Hölder mapping problem basically asks to describe all Hölder mappings from between Karner groups, or say from Euclidean space to a Karner group. And here in the first Heisenberg group, the Subriemannian one, we can extend Lipschitz curves, you know, to almost 1/3 Hölder, and above 1/3, it's actually not possible. Okay. Okay. So yeah. So these are basically the results, and I would like to go now back to the first theorem and explain some ideas of the proof, and then, you know, say a little bit how these elements can be used afterwards for the other theorems that I stated. Okay, as already said, you know, the basic idea is as follows. We take a geodesic triangle and we would like to show that it is thin. So at most as thick as a Euclidean comparison triangle. And first we reduce to the case that gamma is, this triangle is a Jordan curve. This is not very difficult to do. And then we want to construct a minimal surface with boundary this Jordan curve. And we would like to show that, with the intrinsic metric, so basically that's the metric that, is just given by connecting points via curves on this surface, that equipped with this, this is cat 0. And once we have this, then this shows that the Jordan triangle is cat 0. Okay. So in the first step, we have to solve the Plateau problem, the classical Plateau problem of finding minimal surfaces with given boundary in metric spaces, okay, at least with Euclidean isopermetric inequality. Now, for cat 0 spaces, this was already known before, okay, but when you just have quadratic isopermetric inequality, this was not known before. Okay, so we need existence, regularity, of course, as well, and then this intrinsic structure of these minimal disks. Okay, suppose that X is now a proper geodesic and has this Euclidean isopermetric inequality. We take a geodesic triangle, and we suppose, without loss of generality, we can suppose that it's Jordan. Okay, now we try to solve Plato's problem. So what does that mean? So among all continuous maps on the closed unit disk, which are locally Lipschitz in the interior, and which parameterize on the boundary this gamma in a monotonic way, we try to find one with minimal area. Okay, and the following theorem of Alexander and myself says that this is possible. So there exists a map in this family here, which minimizes the area among all maps in there, and which is moreover conformal in the following way. So I already said the metric derivative exists at almost every point. It gives you a semi-norm, and this just says that in every unit direction, the stretch is the same. So just the obvious generalization of what means conformal or weakly conformal, how it's called. Maybe just one word. So really, this is not really the right class to try to solve Plato's problem, right? Because it's hard to verify that if you do the direct method in the calculus of variations, to pass to a limit and then show it's locally Lipschitz. So really, what we do in the background, we use Sobolev mappings, and we try so Sobolev mappings from Euclidean domains into metric space. Shikako Mese has already talked a little bit about those. There's several equivalent theories, one by Curvature and then other ones as well. So we use those. There one has all the compactness theorems that you need. And then we use the isopermetric inequality to show that we have some regularity of such an area minimizer in the Sobolev class, when you have a quadratic isopermetric inequality with this Euclidean constant, it turns out that they're locally Lipschitz in the interior and extend continuously to the boundary. Okay, when you have another constant here, and then in general, you're not going to get locally Lipschitz, you're only going to get locally Hölder, but still continuous extension to the boundary. But then also you don't get this conformality, you only get equality up to a bounded factor, a uniformly bounded factor. Okay. So now we have such a minimal surface or a minimal disk, spanning this geodesic Jordan triangle. And now we take this function here, we call this the conformal factor, okay? And this conformal factor now is, of course, in L2, and it satisfies this inequality here, okay? So on the left hand, so the F squared, this because you have conformality, this is actually just a Jacobian. So the left hand here is just the area of U on this ball of radius R. And the right-hand side, this guy here, this is just the length for almost every R. This is the length of the curve, or U restricted to the boundary of the circle. So this really is just the quadratic the Euclidean isopermetric inequality. Okay. And now one can use this, and that actually goes back to Beckenbach and Rado and Reshetniak. One can use this inequality to show that f has a unique log subharmonic representative f bar. Log subharmonic here means that the logarithm composed, or f bar composed with the logarithm, is subharmonic, so upper semi-continuous, and it satisfies the submean inequality. And then one can define the f bar length. This is this integral here, f bar length of curves by just integrating f bar, and then constructing a function where you take, exactly like the intrinsic metric, but you use this this conformal factor f bar. Okay, and Reshetniak shows that this actually defines a metric. The identity map is a homomorphism, and this space is locally cat zero. Okay, just to say, if you have in the smooth case, right, if you have a Riemann metric, defined by a smooth conformal factor, then the curvature is given by minus 1 over f bar squared times the Laplacian of the logarithm of f bar. So subharmonic means that this logarithm, that the Laplacian is non-negative, so it means non-positive curvature, at least in the smooth case. And Reshetniak shows that this is still true in this. Now, if in the smooth world, we're already done basically, because this y now is really just isometric to the minimal surface with the intrinsic metric, and this is cat zero, and of course extends cat zero to the boundary, and then this geodesic triangle is, unfortunately, in the singular case of a general metric space, we're not done yet. Okay, and the following example somehow shows what is the problem. So take a geodesic metric space, which is obtained from the unit disk. You take a closed interval, and now you shorten the length of this interval. So the metric is, you shorten this little thing, and then you take the intrinsic metric. So locally around the point away from T, or you can even collapse it if you'd like. If you take a point which is not on T, then locally this is just Euclidean, right? Okay, so it's not difficult to show that the identity map is an Airy minimizer, and it is conformal in the sense that I showed. This is completely clear because, it's isometric, locally isometric away from T. Okay, so the conformal factor that we defined is, of course, just equal to 1 almost everywhere, and so f bar is constant 1. So this space y is just isometric to the Euclidean disk, but that is, not that means there's no relationship really between y and this space x here. Okay, so this space x is of course not a counterexample to our theorem, because actually it has a quadratic isoperimetric inequality, but the constant is not 1 over 4 pi. Okay, and this you can see by basically taking an almost isoperimetric region here, right, and then this t is slightly shortened, and then you can show that the isoperimetric constant has to be bigger. Okay, so yeah, the problem really with this space y is that it comes from almost everywhere information, right? So our f is defined almost everywhere. So f bar, somehow represents almost an almost everywhere picture, and it doesn't see things like this one-dimensional thing. So that's why we introduce another space, which we call the intrinsic minimal disk, associated to our Airy minimizer U. This is constructed as follows. On D bar, we just take the function, or the pseudo metric, which just measures the length of images of curves. Okay, and then we take the metric space, where we just identify points at 0 distance. And now we can analyze this space. Okay, firstly, we observe that U factors as a map P, which is just a projection, and U bar, which just assigns to the equivalence class of a point, U of the point itself. This is one Lipschitz. You can see this immediately. And then we show some properties of this space. And again, when you have just a quadratic isoperimetric inequality with a constant which is bigger than 1 over 4 pi, then you get an analogous result where this is replaced by C. So Z is a compact geodesic space homomorphic to D bar. Actually, this projection P, is the uniform limit of a homomorphism. Then U bar preserves the lengths of curves gamma or projections of gamma.
Sorry, I have a question. I didn't get, what are the assumptions on U here? I mean, before there was F, now there is U. I'm a bit confused. Could you, the function U?
So U is our area minimizing disk. So this is the mapping from the disk to the metric space. And F is the conformal factor. So at almost every point, you take the metric derivative in any unit direction.
Sorry, thanks. Thank you.
Yeah. So you have two metrics. That's correct. You have two metrics. One, by Reshetniak's theory, you can show that it's cat zero, right? And now we're doing something else, which is much more related to the geometry of the intrinsic geometry of this minimal disk U. Okay. And yeah. So this is compact geodesic, homomorphic to D. U bar preserves the length, and it satisfies the Euclidean isoperimetric inequality for Jordan domains. Okay, and now what we would like to show is that this Euclidean isoperimetric inequality implies that Z is cat zero. Okay, so once we can show this, then it easily follows that our gamma is actually is no thicker than the comparison triangle, simply because this triangle is, of course, is actually isometric to the boundary of Z, right? So it is a geodesic triangle in Z as well. Okay. Now, how can we do that? So we try to compare these two spaces. Okay, so we have a natural map from Y to Z, which preserves the area. That's not hard to show, and which is also one Lipschitz. Why is it one Lipschitz? Well, if you take 2 points Z and Z prime, you take a piecewise C2 curve, gamma zero, and now you take a bi-Lipschitz deformation of this, and then, well, the length of U gamma T. What is this? Well, this is basically, you can represent it as just, integrating the velocity, so the metric derivative of U along gamma T. But the metric derivative of U, this is just, almost everywhere the same as F bar. So you get this equality for almost every T. And now F bar is upper semi-continuous. So the F bar length of gamma zero is bigger or equal to this lim inf here. So here you take a Tn, a sequence of Tn's approaching zero, where you have this equality here. And then, simply by definition of the du distance, you get an equality here, and that shows you that the length of curves is at most or is decreased at the most, and so you get one Lipschitz. And now you would like to show that actually this natural map cannot contract length. Okay, so in the example that we saw, Z, this intrinsic minimal disk, is actually isometric to the space X. Okay. And there we know that it contracts length, right? So the natural map, because Y in that example is just Euclidean disk, and so this contract length, okay? And we said it's not a counterexample because actually the quadratic isoperimetric, the Euclidean quadratic isoperimetric inequality doesn't hold. Okay, so the idea is basically say, okay, if iota contracts length, so then it has to contract along a curve. It has to contract with a specific factor. Okay, So then we take, well, the tangent cone is at almost every point of the curve. It's a Euclidean cone with angle at least 2 pi. And then we can construct, almost isoperimetric sets. Okay. And now iota preserves the length. So iota of omega has the same Hausdorff measure. Here, this curve, because it's 1 Lipschitz, the length is at least not increased. And this, this red segment, this is decreased by a specific factor, smaller than 1. And like this, you can construct a contradiction to the fact that we said that Z has this Euclidean isoperimetric inequality for Jordan domains. Okay. So that now shows that iota is locally isometric, and thus Z without its boundary circle is locally cat-zero. Okay. And now we would like to show that Z is actually isometric, or is actually cat-zero, right? So we have to conclude this. So we consider the completion of Y. This is a cat-zero space, and we take the natural 1 Lipschitz extension that exists, and then we try to show
sorry,
the same
can I ask
thing.
a question?
Yes.
Can you go back to the previous slide, please? I don't. Why do you get a contradiction? I mean, do you need omega, which basically almost equality in isoperimetric inequality?
Yes, on the left-hand side, yes.
Right.
Side,
where
exactly.
does this come from?
This is basically
why
we
does
have
this
Y
exist?
is a cat-zero space.
Why?
And why?
Yes.
Sorry, why is locally cat-zero? This is basically Reshetniak's theory, right? So yeah, I mentioned that before. So because we have dF bar, right? F bar is log subharmonic, and Reshetniak shows that.
Right, and this is a metric on a disk, so you take like a regular points.
Yes.
Okay.
Yes, exactly. You take a regular point. Yes. Yes. Okay, and now to go to the boundary, we try to do a similar thing. So this works relatively well when you have a rectifiable, when you have a part where the boundary is rectifiable, and when it's the unrectifiable part, this you have to do by hand, and somehow the challenge is, in some sense you should think of Y to be basically the interior, here of an unrectifiable curve, right? And you take so this is cat-zero, and now you take the completion, and you'd like to, yeah. And so this you can do by this. Oh, I don't actually have time. Okay, so let me maybe just conclude by stating three results that use, basically this machinery that we build of solution of Plato's problem, intrinsic minimal disks, and then this. The first one is by Alexander and Stefan Stadler, which shows that when X is a cat-zero space, and you take a continuous convex function on X, which is bounded from below, then you can conformally deform the space by this conformal factor e to the g, by simply taking lengths of curves and just integrating this function, and they show that this conformally deformed space is again cat-zero. And of course, it's very hard to do this with triangle comparison, right? Because you don't really know what are the triangles in this conformally deformed space. And so our analytic approach, you can do that relatively simply. So you start with a geodesic triangle in the conformally deformed space. Now you pull it back via the identity, which is locally by Lipschitz. You fill this with a minimal disk. Right, then you have this conformal factor, this log subharmonic conformal factor, and the completion of this space is cat-zero and majorizes the curve, and then you show that this conformally deformed space still majorizes, And this cat 0, well, simply it's cat 0 because it's the completion of this this d, this distance, where you have the product of two loxoparmonic functions, which is again loxoparmonic. Okay, sorry, my time is over. There's a few more, like not applications, but things that use that. But I think I'll just stop here. Thank you for your attention.